faster, so that point should have been shifted down here, and this point should be shifted down to that intersection. Sorry about that. I hate it when I find my mistake after I've already got the notes on the board. So just take these 2 points and move them down to here. Needless to say though, the temperature, the boiling point temperature has shifted from this spot to that spot, right? And so it's increased. So again, we're seeing that an increased pressure will cause you to have to put more energy into a system in order to drive it from the liquid phase into the gas phase, right? This is true of most substances. I hope I get a chance to correct these notes before I post them. I'll do that. Let's look at how other substances do this. Or not other substances, but water. So, in this instance, for water, the solid phase has the larger molar volume than the liquid, right? Water's that weirdo that doesn't like to do what everybody else does. And so, that VMDP magnitude, the magnitude of the shift with a change in pressure, ends up being greater for a solid than it does for a liquid. In the case of water, the people will behave accordingly. Well, if your initial point of equilibrium, your initial melting point temperature was here, because the solid shifted up larger than the liquid, the new melting point actually moves backward on that temperature axis. And so, remember, these are all saying what happens if we increase the pressure. And so if you increase the pressure on something like water, you actually cause it to melt at a lower temperature than it would have melted had you left the pressure lower, right? Because again, the pressure is going to tend to cause the most condensed state to be favored, and because for water, the most condensed state is the liquid state, you end up being able to achieve that state with less energy dumped into the system. Yeah? When it comes to the gas and the liquid curves, the same phenomenon is observed, and that is that you get an increased pressure increases the boiling point temperature. It's for the same reasons that we discussed last time. All right?
Professor, so for sublimation, you need less energy than for vaporization in water?
Sublimation is going to take more energy than vaporization, because sublimation you have to go from the solid all the way to the gas. But we'll talk about that in moment or three, or later, sometime after I've thought about the question for a second or three. We'll talk more about these phase diagrams in a moment, or not in a moment, but next week or Thursday. But for now, we showed you, using the other graphs, that a change in pressure results in a change in the equilibrium temperature. Right? And these phase diagrams for substances just show, boy, I really should really start labeling my graphs more thoroughly. They just show where the equilibrium between the different phases lies. And what I didn't label here was which phases we're dealing with. So in each of these diagrams, we have the solid phase over here, the gas phase over here, and the liquid phase over here. And each of these curves tracks the point of equilibrium between the two phases as pressure and temperature are allowed to change. And we saw why the equilibrium between phases changes with pressure and temperature. It's, due to this expression. But if you want to map it out in a graphical form, you end up with a phase diagram that looks like this, where each of these curves corresponds to a particular value of pressure and temperature at which the two phases are at equilibrium. When all three phases are at equilibrium at the same time, we lie at what's called the triple point. Past some certain temperature over here, you don't have anything but gas phase. This is called the critical temperature. And what you'll notice is that, this is something I'll do when I have more time, but the slopes of these curves relate to the relative volumes of the phases. So the slope of the solid and liquid curve relates to the relative volumes of the solid and the liquid. The slope of the liquid gas curve relates to the relative volumes of the liquid gas, and the solid gas curve relates to the relative volumes of the solid and the gas. For most substances, you get a curve like this, but for reasons that we discussed, with water, you end up getting a curve that looks like that. And you can differentiate between the phase diagram for a normal substance and a phase diagram for water because of this negatively sloped solid-liquid boundary line. And this makes sense because as we increase our pressure, we end up moving backwards on the temperature axis to find the equilibrium point. And we just showed you that for water, because the molar volume of the liquid is smaller than the molar volume of the solid, an increase in pressure lowers the equilibrium temperature, right? And so what I want you guys to do, for the next day or so, until the next lecture, is to go back and look at all of those diagrams where we plotted the Gibbs free energy versus pressure, the Gibbs free energy versus temperature, and try to relate them to these phase diagrams that we're looking at, right? Because the Gibbs free energy establishes where the equilibria between the phases occurs, and the phase diagrams simply map that out. Okay? So I want to do we've got 15 minutes, I want to do a problem. I'm going to show you guys a problem. I really think that group work is in everyone's best interest. So, when I put these problems up, try to make the most of joining in with people and trying to figure out the problem. And I'll give you a hint. If there's anybody in here who's taken my class already, try to pair up with them because they've already seen a lot of these problems. That's not what I was looking for. Okay, so calcium carbonate has two different forms. One form is called calcite, the other form is called aragonite. And I put this up here and I say at 298 Kelvin, 298.15 Kelvin, I'm going to give you delta H of formation. I'm going to give you the entropy of the substance, and I'm going to give you the molar volume. I also gave you the heat capacity. That's kind of cruel. You don't actually end up having to use the heat capacity with this problem. If you do use the heat capacity, it's a much more difficult problem. And I say first calculate, or would you expect the conversion of calcite to aragonite to be spontaneous at 298 Kelvin, right? You ask yourself that question, and then you answer it. the answer is probably going to be no. And the second question is, could you make it more thermodynamically favorable by changing the pressure, by applying pressure to the system? And so what you're going to do to answer this problem is you're going to, first of all, write out delta G1 for the reaction. And delta G1 is going to be what? What's delta G? Yeah, so I'm basically just asking you here to write delta H for the reaction, write delta S for the reaction, and tell me what delta G is. Yeah? So that's part one. And part two, you're going to write delta G of the second reaction, and remember that we have this expression. This is a constant temperature reaction. And we have the relationship that at constant T, G of T2 is equal to G of T1 plus the integral of V dP from time. We're dealing with solids here, and so in that case, that V is going to be a constant. It comes outside of the integral, and you'll have delta G at T2 being equal to G of calcite. Did I say calcite goes to aragonite or aragonite goes to calcite? Okay, so if it's calcite, did I write calcite goes to aragonite?
Part A.
Yeah, that's what we're talking about. So we're referring to calcite going to aragonite. And so delta G of T2 will be G of the products, so G of aragonite, minus G of calcite. Yeah? G of aragonite is going to be G of T1 of aragonite plus the integral of the molar volume of aragonite dP. And you'll subtract from that G of calcite, which is G of T1 of calcite plus the integral of the molar volume of calcite dP. Right? Both these molar volumes come out of the integral. You sum these up. You just got G of T1 minus, or G of T1 for calcite or aragonite minus G of T1 of calcite plus a term that looks like Vm of aragonite minus Vm calcite and that whole thing multiplied by dP. Yeah? This is just delta G of T1. So this term right here is just whatever term you put here. And so your delta G of the reaction, delta G of T2, is going to be equal to delta G of T1 plus this term that has the difference of the molar volumes times the change in pressure. Assuming the change in pressure is positive, then this term will be positive. The only thing that's going to lower your Gibbs free energy is if this term right here is negative. If this term right here is positive, then the Gibbs free energy of the delta G of the reaction is only going to increase with an increased pressure. So Got a couple minutes left. Take a look at it, and then before we leave, tell me whether or not an increase in pressure is going to make that reaction more favorable.